Hi guys. So today we are going to graph again. As you have done many times this year, we are going to look at our last new parent function and we are going to transform it the same way you have multiple times this year. So this is going to be very similar to what you guys did for your exponential graphs. The only difference is the log function, as we've mentioned before, is the inverse of exponential. So the first thing we're going to do is look at the parent function. So just like it was for exponential, the base actually can be different in values. And what that base is determines the shape of your graph. So as long as that base is greater than 1, and this will happen more often with log graphs. With exponential, you can see that base between 0 and 1 more often. Typically with logs, you really do see those graphs a lot of times with a base greater than 1. But to review, let's go ahead and look at the exponential function. So exponential, those points were 0, 1, because anything to the 0 power was 1. 1 comma the base, 2 comma the base squared, and negative 1 over the base. We also had a horizontal asymptote at y equals 0 because there was no exponent we could possibly raise that function to that would give us a negative number. So as long as the base was greater than 1, the shape of the exponential function looked like this. It had a domain of negative infinity to infinity, but the range was restricted by that horizontal asymptote. So the log function, since it's the inverse, is going to have the exact same points. We're just going to flip the x and y's. So instead of 0, 1, it's going to go through 1, 0. Instead of 1 comma the base comma 1. Base squared comma 2. And 1 over the base comma negative 1. And again, since we're flipping x and y's, that means we're also going to flip the asymptote. And this is very important. Because when it comes to just looking at the general shape of these graphs, it can be kind of hard to tell sometimes after you deal with reflections and things, if the actual just looking at the curve without the asymptote, what kind of a graph it actually is. So it's really important to use the asymptote to help you to determine which type of graph this is. So exponential functions have horizontal asymptotes. Log functions have vertical asymptotes. So vertical asymptote at x equals 0. And again, here's our general shape of the log function. Again, it would go through 1, 0, base comma 1, base squared 2. Again, all those points depending on what your base is, as long as the base is greater than 1. All right, looking at this graph, your domain is from 0 to infinity. And again, that makes sense because we know we can't have a negative argument for our log. So it's going to be from 0 to infinity, and that range is negative infinity to infinity. Keep in mind, this is the inverse, and remember what happens with domain and range on the inverse. They flip. All right, now if the base does happen to be less than 1, between 0 and 1, the points were still the same. That did not change. It was still 0, 1, 1 comma the base, 2 comma the base squared, and negative 1 over the base. It also did have that horizontal asymptote at y equals 0 still. The only difference was the shape of our graph. Because this showed decay, our graph had this direction, went this way. Domain did not change. And then that's my range. All right, so again, log is still going to go through the same points. It's still going to go through 1, 0, base 1, base squared 2, 1 over base negative 1. Those points aren't changing. Still has a vertical asymptote at x equals 0. But again, because now the base would be less than 1, something like 1/2, then let's say I have 1, 0, and then I have 1/2 0, or 1/2 1. If I square 1/2, it'd be 1/4 2. So as those x values get smaller, those y's are getting bigger. And then if you use those negative exponents, it's going to make larger values because 1/2 to the negative second would become 4. 1/2 to the negative third would become 8. So as those x's get larger, those y's are getting larger. All right, domain is still from 0 to infinity, and range is still negative infinity to infinity. All right, so now let's look at some examples. So we're going to start with just a parent function, because again, the parent function has the same general shape, but depending on the base, it's going to go through different points. So these are two common parent functions, just regular log x and then natural log of x. So log x has a base of 10. Remember, if the base is not listed, the base is 10. So I would rewrite this. The points that it goes through are 1, 0, base comma 1, base squared 2, which is going to be way off my graph, and then 1 over the base, -1. Has the vertical asymptote as well at x equals 0. So we'll just plot those points on there. And really the only ones we're going to be able to see well are 1, 0, and 10, 1. But we can still see the shape of that parent function. Domain is 0 to infinity. Range is -infinity to infinity. All right, natural log of x, again, it's going to have the same types of points. 1, 0, base 1, but the base this time is e, which is about 2.7. Base squared, which would be e squared, which is about 7.3. And then 1 over e, which is going to be a little tiny fraction. So we'll go ahead and plot those points. We still have the vertical asymptote. Oop, I missed 1, 0. There we go. So there's the natural log parent function. Again, same shape, just different points depending on what that base is. Domain is the same. Range is -infinity to infinity. And that is a parenthesis, not a bracket on those domains. Because again, it can't actually be 0. It just gets very close to 0. All right, so now we're going to look at the chart that you have seen, I don't know how many times this year. So by now, I know you guys know this, but let's just see what it looks like actually in the log equation. So f of x minus h is a shift right. So if it's a shift right for a log equation, it will happen in the argument. So anything that is in the argument is going to be horizontal. So plus h would be left. A horizontal stretch or compression would be inside your parentheses. Reflect over the y would also be part of the argument. And again, a reflection over the y will look different than a reflection over x. So if this is my parent function, if I reflect it over the y, it'll look like this. If I reflect it over the x, it's going to look almost like your base that's or your base between 0 and 1. All right, vertical transformations are going to happen outside the argument. So it's just log x plus k. Plus k is up, minus k is down. Multiplied out in front is a vertical stretch or compression, depending on the value. A negative out in front, that is your reflection over the x. Again, just like we've been doing all year, we are going to factor out that b value because it makes it easy to see that h and k. That h and k is going to be that first point, that center point that we're shifting. I'm calling it the center of the asymptote. Again, it's not really a center of the asymptote. You're really shifting the new origin. So we're shifting that 0, 0 point because the 0, 0 is not actually on the graph, but it does help us find where our points are in relation to it. So let's go ahead and do some examples. All right, so we're going to go ahead and sketch this graph. So let's go ahead and look at our transformations. So first of all, we know the base. The base is 2. Okay, that's not a transformation. That's just part of the graph. Transformations, we've got a vertical stretch. We've gone left 4, and we've gone down 1. So since we've gone left 4 and down 1, that's your new 0, 0. So I'm going to put a little star there, just like I did for exponential. The only difference for exponential, we went ahead and made that horizontal asymptote. For log, we're going to go ahead and make a vertical asymptote. So because the base is 2, that's what we'll use to figure out our points. Our points, again, they're in relation to -4, -1. So from -4, -1, we typically would go over 1 and up 0. Over the base, which is 2, up 1. Over the base squared, up 2. Over 1 over the base, and down 1. So from that point, we can change any stretches, compressions, reflections. We've got a vertical stretch. That changes our second number. Multiply those by 3. So from that star, right 1, up 0. Right 2, up 3. Right 4, up 6. And then right a half and down 3. And that is my log graph. Domain, again, that's affected by that asymptote. Our domain here is going to be from -4 to infinity. And then all of these will have a range of negative infinity to infinity. All right, let's try another one. Again, hopefully we're used to this by now. That b value or whatever's in front of the x is going to get factored out. All right, so now we can see we've gone left 4 or left 5 and up 4. We have a horizontal compression and we reflected over the x. Remember that 2 is a compression, all right, even though it's larger than 1. So left 5 and up 4, that's going to be our new asymptote or our new 0, 0. We'll make our vertical asymptote there. The base here is 3. And then our parent function points are going to be in relation to negative 5, 4. So from negative 5, 4, I'm going to go over 1, up 0, over the base, up 1, base squared 2, 1 over the base, negative 1. Now we can consider our reflections, stretches, and compressions. Horizontal compression by a factor of 1/2. So we're going to divide all those values by 2. And a reflection over the x is going to make that second column the opposite signs. So I'm going to go right 1/2 and up 0, right 1.5 down 1, right 4.5 down 2. Whoops, that's not 4.5. And we'll write a 6th and up 1, which is going to be pretty hard to see, but we have enough points on here to see our graph. All right, domain here. This is from negative 5 to infinity. And range is negative infinity to infinity. All right, so the last thing that we're going to look at is finding domain without actually graphing the equation. Now, if you want on A, you could go ahead and graph that and write your domain. The problem is something like B, you are not expected to graph this, okay? This is not something you need. B is not something you need to know how to graph. So what we're going to do instead is we're going to solve these algebraically. And the way we're going to solve them algebraically is we're going to take what we know about logs. We know that the argument has to be a positive number, okay? It cannot be negative, and it can't be 0. What that means then is whatever is in the parentheses has to be greater than 0. So all I have to do now is just solve this inequality. Negative 7x is greater than negative 2. So x is, I divide by negative 7, so I'm going to flip that sign. X is less than 2/7. I can go ahead and write that in interval notation, which would be from negative infinity to 2 over 7. And it is going to be a parenthesis because, again, it can't be 0. It has to be greater than 0. So same idea on B. This is not something you need to graph, but we can use what we know about logs to find the domain. The argument has to be positive. So I just need to solve this inequality. So quadratic inequalities, we did these back in first semester. So what we did first was we factored. So to factor this, I need to figure out what multiplies to a negative 18 and adds to negative 7. Well, those numbers are negative 9 and 2. So I'm going to split my middle into those two numbers. I'm going to do my grouping. And then I find my zeros. So my zeros are 3 and negative 2/3. Then I need to figure out when this function is positive and when this function is negative. So what I do is I pick a test point in this little region over here. So any point, like I can pick a negative 10. Well, if I plug in negative 10 and plug it in for x, that's going to give me in the first set of parentheses a negative number, the second set of parentheses a negative number, and a negative times a negative is a positive. So this region is positive. Picking a number in the middle region, okay? It can be anything, like if I pick 0. 3 times 0 plus 2 is positive. 0 minus 3 is negative. And a positive times a negative is negative. Then I pick a number over here in this region, anything to the right of 3. 12, okay? 3 times 12 plus 2 is positive. 12 minus 3 is positive. A positive times a positive is positive. Since the answer to my question is when is it greater than 0, my answer is the positive intervals. So the answer here for my domain would be from negative infinity to negative 2/3, and then from 3 to infinity. So really this question is just a review for you guys from last semester about quadratic inequalities. This isn't as much of a log question as it really is just a quadratics review. All right, so that's it for today for your to-do. Again, a little bit different. Obviously, we didn't do an ed puzzle. We're not going to do an ed puzzle this week just because we're doing graphing and inverses, and you guys have done those so many times this year that I know that I really want you guys to spend the time on these specific functions and not just asking those little introduction questions. Work your practice problems for these. Check your answers. Make sure you show the work on the domain questions at the bottom. Okay, those last two questions show the algebra like we just did in those examples we just did. Then you'll complete the Desmos activity. You can start at slide 8. All the slides before that are just kind of for you to play with and see how that graph changes. This activity is set up a little bit different because it's actually going to tell you if you have your answers right or wrong. Obviously, when you make the graphs in the dotted line, you'll know, but there's some matching questions and there are some multiple choice questions. And it's set up now actually to where if you click the next slide, it'll tell you if your answers were right or wrong or how many you're missing. So that hopefully will help you guys out a little bit. If you need help on those practice problems, again, you can email me, you can fill out a video request, or join the Zoom session on Thursday. If you need a Tuesday Zoom session, then just email me and we can get that scheduled. And then again, you'll have that week 7 assessment. That'll be due by Friday, and that is going to include Thursday's material. If you guys have any questions, again, just feel free to reach out.